next part on Thursday, and we'll go from there. Oh, okay, light is on.
Another quick question. Do we have office hour on this Friday and the next Monday?
Absolutely. And every other day, if you want to come and see me or the TAs, I told them to become available every day, basically, until the homework is due.
Every day?
Every day. Just for you. For nobody else. Okay, all right. All right, so, you know, at the end of the semester, you look back at whatever we did in the course, and in some sense, you say we have done a lot, and in another sense, you say we have done nothing, right? Because in the big picture, really, we have done very little, but the little we have done, I hope, includes enough details that will allow you, with a few more courses, to utilize these concepts for your research. All right, so what I want to do is, I cut and pasted, I think, from maybe the first 8, 9, 10 lectures, 2 or 3 slides that are relevant to for a summary sort of presentation, so let's go through them. So one of the things that hopefully you have convinced yourselves, right, that probability theory, it is extremely simple when it comes to the fundamentals, but what comes out of it can be very complicated, okay? And we haven't done mathematical probability, right? As a matter of fact, my advice will be for each of you to take a course on measure theory, you know, related to probability, because you will find that to be extremely useful in understanding sort of more modern subjects. I'm not quite sure there is such a course at Notre Dame, but you can find maybe a book or an online course and listen to that. So anyways, the 2 rules that I try to emphasize are basically the sum rule and the product rule of probability, and I'm writing this you know, from the early lectures. I mean, later on we will see that this can be densities as well. So this is the marginalization rule, and this is the product rule. Okay, written in 2 different forms depending with respect to what you marginalize, here y and here x. So if you use these 2 rules, effectively, what you can do is you can come up with Bayes' rule, where if you have some evidence of y being equal to little y, you can compute the probability of x being equal to little x. And effectively what you do is you reverse this, and you can interpret this as a likelihood model and you know, as a prior model and a marginalization term on the bottom. And the way it is written here is for discrete random variables. Okay? So this equation, as elementary as it looks, you know, it can lead to high complexity when you try to compute in closed form or in a sample form this probability. Now, the marginalization term, it's also one of the most difficult terms to compute. Okay, it involves extra computation, but is essential for model selection. I have not included in this slides model selection, so maybe on Thursday I will put a few slides to remind you the ideas of model selection. Now, all these equations that you see, really I want you, I expect you, that you should be able to write them down on your own without looking at the books, okay? And I tell you something, I found it rather depressing last year. There's a student from a department that took his qualifying exam with the notes open, had all the notes in front of him, and I was asking, like, write down Bayes' rule, question 1. He just couldn't even find it in his notes. And I got very depressed. Very depressed, okay? And so, in many ways, right, this looks simple. When you look at it, you say, I understand it, but you don't understand unless you can write it using just elementary knowledge. Okay, you need to be able to embed it in your heads. Okay? Now, many other complicated results, I don't expect you to remember them. I don't remember them myself. You shouldn't even make an effort to remember them. But something like this is essential. All right, we discuss independence of two random variables. And so x and y are independent, where the probability of x and y is p of x, p of y. And more importantly, in this course, we introduce what's called conditionally independent random variables. So in this case, given z, x and y are independent. So you can show with counterexamples that if this is true, it doesn't mean that this is true. Okay, so it is very important here to express the conditional independence given z. Okay, and this was very useful in various contexts in this course. Okay, we introduced the concept of random variables, so very elementary. So you can think of a scalar random variable mapping the space of events to the real line. Okay, so you can, omega is a sample, and x of omega is this random variable, right, that takes values little x, but they're real. So you can write the probability distribution for an interval b in the real line as the probability basically of all the events such that x of omega is mapped to the region b. Right? Because in an elementary way, you can only talk about the probability of events. So if you want to talk about the probability distribution of x defined in an interval b, you only have to affiliate this with the events such that x of omega is mapped to that region b. Okay? In some sense, quite an elementary way of defining probability distributions of random variables. And if you take this and you express it as an integral over the domain B of some density, right? We call this the probability density of the random variable x. So in some sense, you need this definition first, and with this definition, then you can extend it and compute, define and compute this probability density little p. Now the notation, again, it's sort of not mandatory, but when you write papers, you really have to be precise. So for example, maybe you don't need to put a subscript capital X. It is implied what variable you mean. But even if you have many variables, you don't have to indicate which variables each probability density refers to. But whatever you do, just be consistent, okay? So this is sort of the most precise way of doing this, but if you don't put the capital X there, it's okay. All right. The definition of the cumulative density function, so I assume you have seen this. And we define moments, such as the mean and the variance, the standard deviation, okay? Elementary things, okay? So you should be able to remember all of these formulas. And I know we kill to death the Gaussians, okay? So this is the univariate Gaussian. And you need to know that Gaussians come all over the place, even if your distributions of interest are not Gaussians, because somehow the central limit theorem leads to Gaussian distributions. Gaussian distributions are useful when you don't have long, fat tails, all right? Otherwise, this is not very useful. And Gaussian distributions are very important to model error. So if you have a model and you say y is some function of x plus some noise, the typical way to add that noise is to assume that that noise is Gaussian. Also, it comes out that the Gaussian distribution is a maximum entropy distribution. And I think I have a few slides on what entropy and maximum entropy means. But basically, from all the distributions that have the same mean mu and standard deviation sigma, the Gaussian distribution maximizes the entropy. Okay? So that's a useful property. We defined covariance. First let me start with the joint distribution of x and y. So you define this again in terms of the events that are mapped to both A and B. You write this with a density, a joint density of little x and little y by definition. And we extend the independence property to densities this way, and the covariance is defined from this nice formula. The symbols again are very important. So for example, if you go and you submit a paper and you don't put the expectation with that exact notation, I will reject your paper, okay, because it's sort of standard now. All right, so the covariance of x and y is defined like that. And we define also the correlation of two random variables x and y is basically the covariance divided by sigma x, sigma y. And if you want to normalize random variables, you subtract the mean, divide by the standard deviation. And okay, so you have seen this. And we define what uncorrelated random variables are. So when the covariance is 0, this is the definition basically of two random variables being uncorrelated. So as you can appreciate from here, the uncorrelated concept is written in terms of expectations, okay? So in some sense is a weaker concept than defining independence between the random variables x and y. So, which means if x and y are independent, they're uncorrelated, the opposite is not true. And maybe in a few papers you will see this concept of orthogonality. All right, so orthogonality, you can think if the expectation of x and y is 0, when you take the expectation of x plus y squared, it looks like the Pythagorean theorem, and that's why we call this orthogonality. All right, I think, I don't know to what extent we cover this topic, right? But we discussed that this, the correlation coefficient between two random variables x and y is really not the best way to express the dependence between two random variables, okay? So in some sense, the correlation coefficient captures if there is a linear relation, let's say, between variables x and y, but when it comes to the slope of that linear relation, you can see from here it doesn't capture that, okay? Also, it does not capture non-linearities between the data, as you can see on the bottom. So this is sort of something that people are talking maybe the last 10, 15 years ago, but you will not see this concept in statistics, because more or less in statistics they are referring to a linear relation, but really in these cases the relations are not linear, so the correlation coefficient doesn't mean very much. So in all of these cases, actually the correlation coefficient is 0. Okay, we define the product rule and marginalization for in terms of densities. So p of x is p of x and y dy. You integrate y out. We define Bayes' rule in terms of densities as well. So can you, I mean, again, I don't even remember if we actually prove it, but can you highlight for me if we can write Bayes' rule in terms of probabilities, how do you get this in terms of densities? Can you think like, you know, I mean, fundamentally we started in terms of probabilities, but now we're writing this in terms of densities. So how from probabilities of events, you know, we go to densities? I mean, can you highlight this? A proof. All right, so basically, you say, I hear you integral. Basically, you say maybe instead of using the density, you can express probabilities over small regions, right? That you write in terms of integrals. and then approximate these integrals as the density times delta epsilon, and maybe the distances cancel out, and you get something like that, right? That's what you're saying? Okay, all right. Don't believe you said that precisely, but we buy that. Okay, so actually the proof of this is two lines, right? It's 2 lines effectively, but it's not necessarily an obvious result. And there is the proof, okay? So I can see your integrals, I can see the little epsilons and the cancellations, etc. So anyways, the product rule, you can use it to express the joint of x and y, and you can write this in terms of densities. So again, remember these equations, the Vegas rule, it's applicable for discrete random variables, for continuous random variables, and you can write these things in terms of densities. Okay. Let me just go directly on the bottom of this slide, right? And this is extremely important result, and somehow on the summary slides I forgot to put the corresponding result in terms of the variance, so you may want to search for it. So a lot of times it's easier to compute the conditional expectation of x given y. So if you want to find the expectation of x, you basically have to integrate y out, okay? So this is sort of divide and conquer type of approach. It looks like the product rule, but as you see here, there is an expectation. So the expectation of x is the conditional expectation of x given y, and then you integrate out y. So you can think of this as, if y was discrete variable, right? You average over all possible values of y, and the averaging is happening with the distribution P of y. We discussed the multivariate Gaussian. Again, you will never claim that the multivariate Gaussian it's a trivial distribution, because everything we do at the end of the day, it seems it's coming from every possible direction, right? So this is very essential. So you need to understand basically everything here. So the covariance basically is symmetric, positive definite metrics. The number of elements to actually compute the covariance, because symmetric is if for x of dimensionality d is the upper, the diagonal and the upper part of sigma, so it's d times d plus 1 over 2. So the cost basically of computing a Gaussian is d squared, okay? So if you try to do some approximations, let's say data compression that is better than fitting a Gaussian, you need to be sure that the cost is less than d squared, okay? This is very important. Okay, and I don't think we need this. All right. This slide is not trivial, actually. And maybe you forgot about it, so tell me what it is. So remember, the probability densities are not functions. So if you have a function f of x and you say, set x equal to y squared and calculate f of y, you use f of x, you substitute x equal to y squared, and you're done. Unfortunately, probability densities, they are not mapped the way functions do, okay? And the easiest way to remember this, how the probability densities map, is to remember that the probability mass written in the x space should be equal with the probability mass written in y space. Okay, so if these are scalar variables, you can see the probability of y is the probability of x dx over dy. And generally, you will have, if x and y are high dimensional, you have the Jacobian matrix there. Okay, this is not a transformation to be taken in a light manner, because it can look a little bit complicated for high dimensional problems, and it is essential. Okay. It comes basically all over the place in modern machine learning and statistics. All right. I don't know why, so I picked up out of my sleep today, different slides that I thought are important, but maybe I'm wrong on the selection of the slides, right? But I saw this definition of the student t-distribution, and I thought we use it in so many different kinds in the course, but it's essential to remember that somehow the student t-distribution, it is really like a Gaussian, but it's actually an infinite mixture of Gaussians, and the mixture comes by averaging with different precisions tau, where those precisions tau follow a gamma distribution. It's literally take all possible Gaussians with all possible taus from a gamma distribution, average them, and that thing will give you basically a distribution that looks like Gaussian, but has fat tails, basically. Okay? So if you have a problem where fat tails are important, so if you want to have a robustness to outliers when you do, let's say, regression, you're not going to use a Gaussian distribution, you're going to use a student t-distribution, and we demonstrated this actually in fitting data with outliers in earlier lectures. You can extend this formula from univariate distributions to multivariate distributions, and the trick is basically the equation that you see on the bottom. Okay, so what you do is you take Gaussians, written in the mean is mu, and the precision is some coefficient eta times a matrix lambda, symmetric positive definite. So it looks like tau, okay? But somehow, to allow this integration, we do this integration in terms of theta rather than in terms of the whole matrix there. So it's sort of a little trick, right, that allows us to use a scalar integration that effectively is like integrating in the precisions, but really we fix the matrix component and we want to integrate on the scalar eta, and the coefficients here are coming basically so you can get similar results as in the 1D case. So this is a nice way. Again, you don't, like this maybe you can remember, this you can, be able to search for it because this is essential as well. Okay, so the student t-distribution looks like this, okay? And this distance that comes up there, it's the Mahalanobis distance. So it's basically, it's what you get with Gaussians, okay? All right. And I think we did so that under which circumstances the student t-distribution becomes a Gaussian, okay? So, in which cases the two things basically give you completely different results. All right. Maybe you remember or not inequalities that we introduced that sound maybe new, but they're very fundamental for error estimations. And the most elementary inequality we introduce is the equation that we see there. So if x is a non-negative random variable and alpha is any positive number, the probability of x greater or equal to a is less than the expectation of x divided by a. What I want you to appreciate about this equation that is applicable to any non-negative random variable, all right? We don't say what type of distribution, and for any alpha. So this is very general, okay? And if you extend this, and instead of x, you have a function of x, f of x, you can generalize this and say the probability of f of x greater or equal to alpha, less or equal to the expectation of f divided by alpha. And if this equation, again, looks to you useless, what you can do is, if you put f of x to be x minus e of x squared, you get the Chebyshev inequality. But more or less, you can, with some rescaling, you can look at it in this form. And it says the probability of being away from the mean by a distance epsilon times sigma, where epsilon is really arbitrary, is less than 1 over epsilon squared. So the probability to be away from the mean, let's say by 2 standard deviations, is less than 1/4. This is significant. Maybe this 1/4 it's a useless number, right? It's maybe not, I mean, when you try to bound something, if I give you and say, oh, this is less than infinity, you say, who cares? And I mean, in some sense, 1/4, it's just maybe too big a number. Maybe not very realistic, but the point is, this equation here, it's applicable for any distribution, for any random variable. Okay? And again, if you get involved with approximations in modeling even rare events and things like that, these distributions, these approximations here are extremely fundamental. So we do not yet make use of them in this course, but they are extremely, extremely powerful because they are general. Okay, and I think we generalize these things by using the, let me put both of them up, the weak law of large numbers and the strong law of large numbers. So what we did is we formed, if we have realizations from any distribution that has a mean mu and a variance sigma square. So, and the key ingredient here is if xi are samples basically from any distribution with mean mu and variance sigma square, then once you form the sample mean, the probability of the sample mean being away from the actual mean by distance epsilon is 0 as n goes to infinity. Okay, and you can write this as a limit in terms of probabilities, or directly that the limit of xn is equal to mu almost surely. And another way of writing this is also that the sample mean follows a Gaussian distribution with mean mu and variance sigma square over n. This is actually something that non-Bayesian people will write, so be sure that you understand there's nothing Bayesian about this formula, right? This is a frequentist sort of calculation. It's fundamental to probability theory, but there is nothing, there's no Bayesian or anything like that in the nature of this equation. Okay. So this is extremely important, as we have seen for Monte Carlo approximations. And again, what is important here is that the sample mean follows a Gaussian, and it doesn't really matter from what distribution x1, x2 to xn have been sampled from. Okay? And now you appreciate again why Gaussians are very important. It's not an accident in life, right? That we keep talking about Gaussians, because you can have any arbitrary distribution. If you form the sample mean, it gives you a Gaussian distribution. Very briefly, we discuss a little bit about information theory. As I told you, if you are interested in the subject, and there is a whole sequence of online videos from David Mackay, and his book is freely available, that you can learn everything you want about information theory. And you will also see in those video lectures the relation of information theory with Bayesian inference. So it's sort of the benefits are multiple. But so what in the context of information theory, we want to know how much information we learn when we observe the value of a random variable. Okay, and we basically said that something that is very probable provides little information. So if you have a distribution that is picked and only takes one value, right? You're not learning anything, okay? And also we agree that if we have two events that they are unrelated, the information that we learn observing x and observing y should be the information that we learn when we observe x and y, okay? And somehow we try to relate this equation here with the independence of two random variables, and from there we can extrapolate actually that h is somehow related with the log of the probability, maybe with a minus sign to account for that. And this is the definition of the entropy we got, okay? Is minus the log of p of x Traditionally, this is expressed with the basis for the logs 2. The units that you use for entropy is bits. Okay. Here is for one value of the random variable x. So what we need to do is to define the entropy. We basically have to average. So for a discrete distribution, basically, if we take this information that we learn when we observe little x, and we average with respect to the probability of x, you get the entropy of x for discrete distributions. And you can generalize this to, you can substitute this with an integral, basically, and get the entropy of a continuous variable. You can actually do lots of calculations and compute maximum entropy distributions. There is a wonderful book, actually, that's freely available online. That is most probably one of the most refreshing reads on probability theory. It's written by a physicist, Jensens, that it's all about maximum entropy and why maximum entropy comes in every subject in science, basically, from weather prediction to biology to ecology to engineering, to the stock market. So it's everything he has in his book is about maximum entropy. It was a concept that it was considered useless. So when he was a professor, I think at Wisconsin, and was submitting papers, all his papers were rejected one after the other. And only after he died, his students published his book, and now, everybody talks about maximum entropy. Okay? But at his time, everybody thought maximum entropy is baloney. Maximum entropy, by the way, distributions are used also as priors. We do not emphasize this in the course. So really, if you have some constraints on the random variable, but you don't know anything else, the best you can assume as a prior is a maximum entropy distribution. And it comes out that the maximum entropy distributions are in the exponential family. So the exponential family is an ideal way to introduce prior models. So the maximum. So if you have a discrete distribution that can take m values, we proved that the maximum entropy distribution is 1 over m. Actually, you expect that answer, right? It's the uniform distribution. You can actually prove something very nice, that for any discrete distribution that takes, for any random variable that takes m values, not the uniform, but any discrete distribution, the entropy is less or equal than the log of mu. And the calculation is extremely trivial, because for any distribution, this is the discrete, this is the definition of the entropy, okay? And I can put the minus sign and write this log as log of 1 over p. And here, I'm doing what? Remind me, what is this inequality here? That this summation is less or equal log of the summation. I'm moving the log outside. What allows me to do that? Jensens inequality, which is the most important trick in probability theory that I know. Okay, the most important trick, right? The Jensens inequality, I think it's on the next slide, is for convex functions, and minus log is a convex function, log is a concave function. So you can do this, and so you can remove the log outside. All right, so here is like having the expectation of a function. So this is the function of the expectation, okay? And p and p cancel, and the summation will give you m. So h is equal to log of m, which also you expected because the entropy of the uniform distribution, which the maximum entropy is that, all right? But here is an alternative, if you like, an alternative proof. So this is Jensens inequality on the top. Is what I just mentioned before. For any convex function, f of the expectation of x is less or equal than the expectation of f of x. Written here in terms of continuous, variables. F of the expectation is this integral, less or equal the expectation of f of x, which is this. Okay? And just to get you a sense of another way where Jensens inequality comes, if you remember, we define this very important quantity here, which is what? What is this thing here? The KL divergence. And what is the KL divergence? Remind me, I forgot.
How similar to probability distribution?
Yeah, so basically you're measuring the distance between two distributions. You can think, let's say, P is the exact distribution, Q is an approximation, and you say, you know, if you try to approximate, let's say, some arbitrary distribution with a Gaussian, and you try to play with the mean and the variance of that approximation, you try to find mu and variance so that this KL distance is minimized. So KL distance is measuring the distance between distributions. It's really not a true distance the way we know it, okay? And it's non-symmetric. Some people will say, well, that's bad news. But actually, you can take advantage of the non-symmetry. So the KL distance between P and Q is not the same as the KL distance between Q and P. And if you use the two, you get, you know, if you use each of them, you come up with completely different algorithms. And we will see some of this next semester when I do variational methods to approximate implicit distributions. Different approximations when you reverse this. So anyways, what I wanted to show you is using the Jensens inequality that the KL distance between P and Q is greater or equal to 0, right? It's a distance, you expect that. And so here is the simple proof. The KL distance is by definition what you see here. And minus log is a convex function. So from the Jensens inequality, I can move the function out, so minus log is out. And then I have P times Q over P. P and P cancel. The integral of Q is 1 if it's normalized. So log of 1 is 0, so the KL distance greater or equal to 0. Okay? Now, do I expect you to remember this definition? Yes. If you forgot, you know, in 2 weeks from now what the KL distance is, then, you know, we all failed. I failed in emphasizing how important it is, okay? Because we don't really, I mean, there are many, many measures for distances between distributions, and this is the simplest. So people, for example, who work on network theory, on different type of networks, and they have to define distances, you know, in a discrete manner, if you like. This distance has been shown not to be a good measure between two distributions, all right? But somehow, this is the first thing you should try when you talk about distances between distributions, okay? And it comes out, there are generalizations of these distances that you may see in machine learning books. So one way or another, this is the starting point that you need to know about. Okay, and obviously, if the two distributions are the same, then the KL distance is 0. All right, we define also the conditional entropy of y given x. All right, so this looks like the definition of the you know, the entropy that we have seen. The only difference, and I emphasize this with a circle here, when you average, you don't average with a conditional distribution, you average with a joint distribution of x and y. Okay, so the way the conditional entropy is defined is, you know, so this is the entropy of y given x, and here you just need to remember that you use the joint distribution of x and y. So if you plug in the joint distribution of x and y using the product rule that you see here, you actually get a common sense answer that the entropy of x and y is basically the conditional entropy of y given x plus the entropy of x. Okay? which is sort of expected, is like what's the average information that X brings in the picture, and then the information given X that Y brings. Okay, so you have this this nice equality here. And since we talk about the independence of event, I want to bring back something that we all forgot, all right, because we didn't really use it in this course. So we said that, you know, for, let's say, in terms of densities, X and Y are independent on the joint density of X and Y is P of X times P of Y. So how do we actually, what is a good measure to express the independence of random variables X and Y? And that very good measure is the mutual information. And the mutual information is nothing else but the KL distance between the joint distribution of X and Y and P of X times P of Y. Right? You remember independence means this equal to that. So the mutual information is basically the KL distance between the two. And this is extremely fundamental. So if you're going to try to express, you know, the independence of two random variables from collections of data that you have, the best way to do this is using the mutual information that you see here. Okay? And if you remember, and I remove it from the slides, when we covered this lecture, there is a discretized form of this mutual information that is basically is sort of the practical way of implementing this integration that you see here. Okay, and that discretized version basically accounts for whatever discretization you use for X and Y. Okay, because, you know, if you have a continuous distribution, you're going to have to sort of use different bins and see how many data you have on the different bins. So you're going to need some discretized version of this, and that leads to some modified definition of mutual information. But if you remember this definition, basically this is what you will need to do to say something about the independence of X and Y. And actually, a very nice and sort of intuitive result here is the mutual information between X and Y is the entropy of Y minus the entropy of Y given X. Can you appreciate this? Right? This is, in average, the information that you get from learning Y, and this is the average information you get about Y given X. And if the two things are zero, means knowing X doesn't bring any information about Y. Okay? But somehow, this simple equality here comes from the definition of the mutual information that you see on the equation in the middle. All right. So we started talking about Bayesian things. The notation here is a little bit primitive, but let's make sense out of it. So X is the data, H is a hypothesis, or it can be a value of a parameter, or something you want to test. So this is the posterior for this hypothesis H given the data X, and we wrote this as the likelihood, all right? So you can think the likelihood is the forward model. If you know that the hypothesis is correct, what is the probability of X times the prior divided by some normalizing factor, okay? We discussed about different type of priors that we need to use. The likelihood, I want you to see it not as a function of X, all right? It's a function of the parameters, in this case of H. So lots of books and lots of statisticians will not write this as f of X given H. They will write it the other way. They will say f of H, you know, slash X, whatever, to emphasize that we treat this as a function of the parameters, not as a probability of X. So the normalization factor extremely significant when it comes to model selection, right? And also very significant from, from computing. So in statistical mechanics, you will see that lots of thermodynamic properties are basically computed by this normalization factor. All right, so this is sort of in the heart of many important questions in statistical type of calculations. Okay, so the only thing you need to remember here is that in the normalization factor is the prior that comes in, not the posterior, right? So this, basically the whole thing has to integrate to 1 for this to be properly normalized. So the numerator is unnormalized posterior, so obviously the denominator has to be the integral of the numerator in the theta space, okay? Here I remove the h and I put theta directly to just to make things clear. All right, we discussed point estimates, all right, extremely important. The map estimate is the parameters theta that maximize the posterior, and usually when you do this type of problems, you work with log probabilities. So the theta that maximizes the log of the posterior is the map estimate. We also define the posterior mean, and you can also define quantiles. Okay? If you do any of the above, don't say that you do Bayesian statistics, right? These estimates are not considered Bayesian. Okay? Sort of, yes, you use the posterior, but you use a point estimate, and if using a point estimate, you're not fully Bayesian. So if you want to be fully Bayesian, you need to be able to actually do predictions. So here is, if you already have observed data x, what's the probability now that you will observe x hat? All right? So this is, you already have observed x, and now you're asking what's the probability of observing x hat. And it comes out the calculation in some simple manner is nothing else but the likelihood times the posterior with the parameters integrated out. And you notice, this looks like the normalization factor in the Bayes rule. The only difference is in the normalization factor in the Bayes rule, we have the prior, here we have the posterior. Okay? So this is, if you do this, then you're Bayesian. Because to be able to calculate this integral means you need to calculate the whole posterior and somehow being able then to approximate this whole integral using the posterior. And one of the ways we did this later in the course was using Monte Carlo approximations. Okay? So do you have to remember this formula? Yes. Because it's sort of like, it's in the heart of doing Bayesian analysis, right? You need to remember that this is nothing else but the likelihood times the posterior with the parameters integrate out. So this is sort of like model averaging, right? So you say, there's no parameters there. So the idea here is, I am going to average, the probability, the values of x, the probability of x hat, but because I don't know parameters, I'm going to average it with all possible values of theta that are coming from the posterior, because you already know the posterior since you already have collected data x. I'm just very briefly, I'm going to show you this calculation for this Bayesian calculation for a multivariate Gaussian case. Many of the results that you see in the notes, they are in the literature, right? But you have to trust me that you're going to have to search very hard in 20 books to find those formulas. Okay? So now you have them in the notes, so take advantage of that. Okay? And if 10 years from now you find some mistakes, don't send me any corrections, because by then I will have no interest to change those formulas. So send them to me, next month or something. Okay? Because I am sure there must be some typos in these equations. Okay, so what is the idea to apply Bayes' rule on the Gaussian? So what I did is, let's say we have collected n data points from a multivariate Gaussian with mean mu and precision lambda. And so we want to do a Bayesian inference now on mu and lambda. You can do on all combinations of mean and variance and all of these things. But here we're going to do in terms of mu and the precision matrix lambda. So if we're going to do this, we need a prior model. And we already have discussed this both in the 1D case and the multivariate case. The nice conjugate prior is to take a conditional prior of mu given lambda to be a Gaussian, the way that you see here, all right? And then take for lambda to be a Gaussian distribution, and a Gaussian distribution is basically a distribution over positive definite symmetric matrices. Okay? So the distribution of mu and lambda together is a normal Gaussian distribution. If you search on Wikipedia, you will see it says normal Gaussian, but here we write it explicitly as a normal times a Gaussian distribution. Okay? And there is meaning basically you can assign, because this in the exponential family, you can assign meaning to the different, to nu and tau and mu zero and kappa there, but we leave these things out. So for now, you treat this as a conjugate prior that somehow will, hopefully, if we do the algebra correctly, it will give us a posterior for lambda and mu. That is also going to be a Gaussian Gaussian distribution. The only difference will be that these parameters nu and tau, nu, yes, and tau and mu zero and kappa, we have to be updated to account for the fact that we have collected this data. So if you do the algebra, you can write the likelihood like this, right? You multiply basically multivariate Gaussians over the data points n1 to capital N. Okay, and you should sort of be familiar with these calculations. This matrix here, S, X bar, anybody remembers what says X bar? S is always the scatter matrix, right? The summation of the data points of xn minus X bar times xn minus X bar transpose. So the idea here is you take the distances of the data points xn from X bar, which is the sample mean. Okay? So that is the scatter matrix defined around X bar. So that's the likelihood. This is the prior, and the prior we said is a Gaussian times a Gaussian distribution. The normalization factor for these distributions is known. Okay? So when you multiply the two, eventually you get, what is the eventually? Tell me when you say eventually. Eventually is here. So eventually you get that the posterior is a Gaussian times a Gaussian distribution, and you notice the only thing that has changed is the mean has been updated. From mu0 now you go to this to account for the fact that you have some observations. Tn has been updated. Okay, and again, Sx is this scatter matrix, and this counts nu n and kn have been updated from mu0 and k0 to account that you have collected n data points. So this is actually a very nice example to see this Bayesian formula working for this type of estimation for a multivariate Gaussian. But keep in mind that generally speaking, right, you will never be able to do these calculations analytically. Right? You'll never be able to write things in such a nice form. But I can also say, if you can write them in this nice form and you don't, and you say, no, I'm going to write a computer code to this, that's not good. There is an analytical solution. You should know that there is an analytical solution. Okay? And I think certainly I would like to believe that, with at least, with some minor, a few minutes work, you should be able to do this calculation, because all the formulas, nothing to remember, it just multiply the Gaussians, multiply with the prior, and you rearrange, and when you rearrange, you basically get a posterior that looks in this nice closed form. Okay, and if you think about it, just amazing that you can get these updates in such a nice form that is sort of appealing, basically. So you can actually get the since this is a Gaussian wizard distribution, you can get a normalization factor as well analytically, all right? That's the normalization for the prior, that's the normalization for the posterior, and you can see again, the only thing that you have to update is this counts nu n and kn from nu 0 and k0. For this particular problem, it comes out that actually you can even compute the posterior marginals. This, in many times, right, it's a very essential calculation. For example, if you want to do an estimate, let's say, of the mean, you may want to, how do you, if you want, somebody tells you, can you tell me what is a good estimate of the mean? You're not going to use basically this posterior to compute an estimate of the mean, because this is the joint posterior of mu and lambda. So if you want an estimate of the mean, what you really need to do is you need to integrate from that posterior that you see here, lambda out, and find the marginal posterior. And the marginal posterior in this case comes to be a student t distribution, and the marginal posterior of lambda comes to be a wizard distribution. So actually, if you come up with this distribution, then actually you can give an estimate for mu, say it's the mean plus minus 1 standard deviation, and that's what's actually reported in the literature in statistics books, okay? So if you want point estimates with error bars, you're going to need the marginals of mu and lambda, not the joint posterior. In this case, you can compute the marginals. In other cases, that may not be possible. You can, for this problem, you can do lots of different type of calculations in closed form solutions. So if you want to find the map estimates of mu and lambda, so if you want to maximize the joint posterior, here are the map estimates. You can, from there, actually, you can test them that they're correct. If you have no data, basically, you can recover the MLE estimates, and so that's nice. All right. This is a very busy slide. Does any of these things resonate, or we forgot everything? Does it, does it look another course? What do you think? Huh?
It rings a bell.
It rings a bell. Yeah, but there is a movie that says something about ringing a bell, and it was referring to somebody who went crazy. And I don't remember if it was a questions, right? Okay, so, all right, so let's ring a bell. One of the calculations that I am not going to explore on these review slides, right? But is to calculate this marginalization factor in Bayes' rule. So if we have, let's say, in this Bayesian inference problem for the mean and the precision, right? I write the posterior is the likelihood times the prior divided by the probability of the data, right? That's the marginalization factor. So we did a lot of examples on computing the probability of the data, that marginalization factor, because P of D is the starting point to do what? I mean, why do we care to compute P of D? Because P of D is needed where? In what major task do we need P of D? Model selection. Everything to do model selection has to do about P of D, okay? And so I cut and pasted this slide because it was convenient, because to demonstrate to you basically that what you need to compute P of D, right, is if you know the normalization factor for the posterior,
and I call that normalization factor Zn. If you know the normalization factor for the prior, and I call this C0, and if you know the coefficient that you get in the likelihood, that in this case a Gaussian, you get something like that, then plugging in this from this equation, you can get P of D given by this nice, wonderful formula, which, as complicated as it is, it's really one line of programming to be able to compute P of D, and that will allow you to do model selection, okay? So the idea is, again, how do I get this P of D with this normalization factors? Everything, if you plug in things here, right, you will have terms that involve mu and lambda, and then some coefficients, and then terms here that involve mu and lambda, and then some coefficients. You get rid of all the terms with mu and lambda because they cancel out. What is left is this equation, and this equation gives you basically the normalizing factor that is the starting point for doing model selection. Okay? And again, it looks weird because you have this multivariate gamma functions and these determinants, some powers, and etc. But this is what it is, and that's the, again, if you have that formula to plug it in the computer, it's one line. Okay? And that will allow you to calculate P of D. All right. We have 14 minutes, so we can briefly review a little bit the exponential family as well. So why do we care about the exponential family of distributions? Because sort of with one equation you can include many, many distributions together, and you can actually derive all the formulas for all of these distributions together. And you may be able to actually formulate your problem with sort of an exponential family for the likelihood and the prior, and which guarantees that the posterior will be also in the exponential family. So that is sort of wonderful, okay? So what is the definition of an exponential family? Is the equation that we see here. Eta are basically the natural parameters of the distribution. U of x are the sufficient statistics. Some function of x basically that is needed to compute this distribution. H of x, another function. G of eta is basically a factor here that ensures that the whole distribution is normalized. Some definitions that we use is, we wrote minus log of g to be a, okay? And we also introduced the partition, the normalization factor z as 1 over g, right? Okay? Because usually we like, the normalization factor to be on the denominator, so z equal 1 over g, a equal minus log of g. So minus log of g means log of zeta, and you can see the normalization factor basically is the integral from there of h of x times this exponential dx. So this is a very difficult term to compute, okay? Computationally, this is a very difficult term to compute, but as I told you, it is the normalization factor that contains most of the physics of these problems, okay? So I know there are some students from chemical engineering, etc. You will see that you won't be able to do much in computing properties of materials, let's say, from statistical calculations unless this type of integrations can be done one way or another. Very essential. Okay, so this exponential family again is h times exponential of eta transpose u divided by z, where z is 1 over g. Okay, so sometimes these natural parameters theta depend on some other parameters theta, so you can actually think of everything as a function of theta. Basically the same equations rewritten. Okay, the second equation here is basically what I have done is I took this g and I put it inside as minus exponential of minus a, because you remember what's the relation of a and g? A is minus log of g, all right? A is minus log of g, so minus and minus an exponential will give you back g, okay? So this is an alternative definition of the distribution. Okay, I'm not going to do all the algebra again, right? But let's, we're going to introduce a problem that has a likelihood in the exponential family. We will put a prior also in the exponential family, and the posterior, basically in a unified way, will be in the exponential family. So we take the likelihood to be like that, okay? This is, I'm writing it for one data point. And we're going to write a prior also in the exponential family. So we are going to write it as g to some power, okay, times an exponential, which will be eta transpose, times some coefficient tau 0, okay? And I am not going to go through all the scaling, but somehow to make things more looking nicer at the end, we wrote tau 0 as nu 0 tau 0 bar. So the prior is written in this form, okay? You will see from the results why this is sort of convenient. If you don't do this to start with, at the end, you will see that somehow the algebra will tell you that this is a preferable way of writing the prior, okay? So anyways, and so what is the posterior? The posterior will be this, all right, times the prior. And, okay, let me see now what is happening here. No, this is, we're still at the prior here, okay? So we're going to assume that we have a data set x1 to xn from this likelihood. We're going to multiply with this prior, and let's see how the posterior is going to look like. So this is the likelihood, all right? So I took basically that each point comes from the exponential family that you see inside this product. So when you expand this, you have the product of this h of xn over all n's, then you have g to a power n, and then you have exponential of eta transpose, and then this product with exponential becomes a summation over all the u's. All right? So basically, this is the sufficient statistics for your data set. All right, so you don't really need to know the individual ux1, ux2, etc. You need to know this summation. And the interesting thing is the size of the sufficient statistics does not grow as the data set grows. All right, so this is very important in the exponential family because the size of the sufficient statistics is basically controlled by the dimensionality of eta. So this is the likelihood. This is the prior. You multiply them, and at the end of the day, there is the answer. The answer is the posterior is also in the exponential family, and the only thing you need to do is update this coefficient nu 0 and the tau 0 to nu n and tau n, and here are the update formulas. Okay, so nu n is nu 0 plus the number of data points. Tn is what you see here. Okay. And nu n times tau n bar, you can actually appreciate why I did this because u bar is actually, when you write it like that, u bar is the sample mean of the sufficient statistics, okay? So it is this summation divided by n, all right? So in some sense, when you write it like that, you can see that nu 0 and tau 0 in the context of priors play the same role as n and u bar. So basically this is like having nu 0 prior measurements of value tau 0 bar. Okay? So and again, the algebra is not very important. What is important is that if the likelihood and the prior are in the exponential family, then the posterior is in the exponential family, and everything, it is known in a precise form, including the normalization factor z. And a calculation just to get you a sense on how powerful these methods are in the exponential family, right? I can write down the predicted distribution for any for any distribution that fits in this family of these exponential distributions. And so if, let's say, you have observed data x, and you want to ask what's the probability of observing data points x prime, again, remember the predicted distribution is the likelihood, if you knew the parameters, times the posterior, with the parameters integrated out. So when you do this calculation, you get a wonderful formula that says that the predicted distribution is nothing else but this normalization factor divided by that normalization factor times some scaling that depends on the data. So basically, you have the predicted distribution written down for any distribution from this family, from this exponential family. Okay? So with one formula, you can actually solve many, many problems at once. Okay? You remember any of these things? Was this class or it was 2 years ago? I forgot. Does it make any sense? A little bit. Okay. All right. I'm actually was going to do a regression problem because when we did it, we did it with the exponential family before we formally discussed about regression. So I told you I was going to come back to redo it so that I can remind you how things fit together. But so let's, we have 4 minutes. Let me give you some fundamental results out of the exponential family. So the first result is that the expectation of the sufficient statistics is actually the gradient of A with respect to eta. You remember this formula? So if somehow you can compute A, which is the log of the normalization factor, right? If you can compute this analytically, then the gradient of A is actually the expectation of the sufficient statistics. Right, so if you want to compute them, if let's say the sufficient statistics, let's say of u of x is x. So if you want to compute the expectation of x is nothing else but the gradient of A with respect to eta. Wonderful result, okay? And it's applicable to any distribution in this family of distributions. And actually you can push this further, and if you want to find the covariance of u of x, it's nothing else but basically the second derivative of A with respect to eta. And because the covariance is positive, you can conclude actually from this formula that A is a function of eta is a convex function. Okay, A is a function of eta is a convex function. By the way, you can continue these formulas, but usually you're happy with the mean and the covariance and you don't want to go any further. But again, if you need to compute higher order moments, you can do this as well by further differentiation. So let me motivate this moment parameterization, right? So when we started the course, we were giving every distribution, we said this in terms of the mean, in terms of the variance, like the Gaussian. So that's what we call a moment parameterization. But what you see here, there is no moment parameterization. This is in terms of natural coordinates eta, right? I mean, there's no moments here, right? So this is not the way that you write typically, let's say, Gaussian, right? This is very different from the classical way that you see in textbooks. So what's the relation between this natural parameterization and the moment parameterization? Well, the relation is 1-to-1. And the way to see this is the following. We didn't prove, but we proved it in an earlier lecture, that the exact, let's say, moment mu, which is the expectation of the sufficient statistics u of x, is the gradient of A, right, with respect to eta, correct? Now, A is a convex function. So if you look at this equation, what it means is there is a unique map from mu to eta and from eta to mu. So if you write the distribution in terms of natural coordinates eta, there is a unique way to express this directly in terms of moments. Okay? And the other way around, if a distribution is written in terms of moments, you can actually reverse it and write it in terms of eta. So this mapping from eta to mu and mu to eta is basically invertible, and this is very significant, okay? Because it sort of allows us to use one parameterization or another in a completely equivalent form, and which one we use, it depends which one makes our problem of interest easier to solve. And many problems that look to be convenient in the moment form, actually it may be way more convenient in natural coordinates, okay? And one of those problems is the problem with doing regression for generalized linear models. It's 1:45. I don't have time to discuss this now, but I am going to leave you with this picture. So if you want to look back in the slides in an earlier lecture and see what it was all about, somehow it was a very general way for doing regression with generalized linear models for the exponential family, and so we will discuss this on Thursday a little bit, and so I'm going to leave you there for today. Okay.
肯定是 update。那你
这
要不
个我知道是 update 是在哪一步 update？ 是 resample update 哪一步，还是说就是 normalize weight 哪一步？